Okay, now we're going to look at derivatives of exponential functions. Remember that an exponential function is a function where our base is a constant and our variable is an exponent. Here are some examples of exponential functions. So we are going to be looking at the derivatives of exponential functions. First, you need to familiarize yourself again with your rules for exponents. We will be using some of these rules not only in this section but in other sections. The first rule is that the product of two exponential functions, notice the bases are the same, a to the x and a to the y, we find that product by adding the exponents. When we divide, as long as the bases are the same, notice they're both a, we subtract exponents. When we raise to a power, we multiply exponents. Numbers 4 and 5 are a special part of the product rule. 3, 4, and 5 are all product. I'm sorry. 3, 4, and 5 are all power rules. The rule 4 tells us that a to the x times b to the x is the same thing as a times b raised to the x. Now a to the x divided by b to the x is the same as a divided by b raised to the x power. Now, in this particular section, we're going to focus on e to the x. E to the x is a graph that has a special property. The slope of the tangent line to the graph, where it crosses the y-axis, is exactly 1. If we have a smaller base like 2, our slope is less than 1, and when we have a larger base, our slope is greater than 1. So e to the x is a special exponential function. It also has this property. The derivative of the natural exponential function e to the x is e to the x, so its derivative is itself. Now we want to find the derivative of e to the negative x. Well, if we're going to find this derivative, the first thing I'm going to do is I'm going to remember what negative exponents mean. That means this is the same as 1 over e to the positive x. If I write this using this type of a notation, then I can apply our quotient rule. The quotient rule tells us low, which is e to the x, d high times the derivative of 1 minus high, which is 1, times d low, derivative of the denominator. Down below, the square will go. So then we're going to take e to the x in the denominator, and we're going to square that. Well, e to the x times the derivative of 1. Since 1 is a constant, its derivative is 0. Minus 1 times the derivative of e to the x, which we said is e to the x. And remember our rule from a second ago, when we raise to a power, we multiply exponents. So x times 2 is 2x. Now in our numerator, e to the x times 0 is 0. So we have negative 1 times e to the x is negative e to the x in the numerator. And we have e to the 2x in the denominator. Now here is another application of the rules we looked at earlier. Notice we have the same base on top and bottom. So we can just subtract exponents. 2x minus x is 1x. So we will have e to the x. That e to the x will actually be in the denominator, since 2x is larger than 1x. So we'll have negative 1 divided by e to the x. We can leave it this way. If we want to go back to using negative exponents, this is negative e to the negative x. So the derivative of e to the negative x is negative e to the negative x. In a later section, when we look at the chain rule, we'll find an easier way to find this derivative without using the quotient rule. Now we want to find the derivative of 3x squared e to the x. Notice that this is a product. So when I go to find the derivative, I take the first function, 3x squared, times the derivative of the second function, which is e to the x, plus the second function, which is e to the x, times the derivative of the first function, which is 3x squared. Then I have 3x squared times the derivative of e to the x, which we have said is e to the x, plus e to the x times the derivative of 3x squared. Remember, we make the 2 a coefficient. 2 times 3 is 6. Subtract 1 from the exponent, so we have x to the first power. So this is 3x squared e to the x plus 6x e to the x. Now, notice in this section that we only looked at the derivative of e to the x. We'll have to look at the derivative of logarithms in